Okay, let's talk a little bit about acids and bases. We know acids tend to taste sour. Think of vinegar or a lemon. It has a lot of citric acid in it. It tastes sour. Causes dyes to change color. Bases tend to taste bitter and feel soapy. And soaps will generally test basic. An acid will turn blue litmus paper red, and a base will turn red litmus paper blue. But that's sort of an either or test. According to Arrhenius, the acids will increase the H plus concentration in the solutions, and bases will increase the hydroxide ion concentration in the solution. According to Arrhenius, an acid will react with the base as follows. The acid plus the base will produce a salt and water, and you should remember that from your first semester chemistry. For example, hydrochloric acid reacts with sodium hydroxide to produce sodium chloride and water. The problem with the Arrhenius definition is it tends to confine us to aqueous solutions, and so we'll need to consider some broader definitions. Okay, so let's talk a little bit about Broncillary acids and bases. That's a little bit different definition. So in this case, the hydrogen ion is simply a proton with no electrons. Remember, hydrogen has one proton and one electron, no neutrons. In water, the H plus forms clusters, that is, it associates itself with water molecules. The simplest of those clusters is H3O plus, or the hydronium ion. And we'll largely consider H plus associated with water as H3O plus. We can form larger clusters, H5O2, H9O4. A lot of times people will use the H plus and H3O plus interchangeably. However, realize in aqueous solution, the hydrogen ions associated with the water, and so you're likely dealing with hydronium H3O plus, and most people will want to write it that way. And you can see these larger clusters below, where you can see the H3O plus, but then it's more loosely associated with other waters. And those dotted lines indicate a loose bond, or what they call a coordinate covalent bond, in which one of the atoms in the bond donates both electrons instead of one electron coming from each. So if we focus on the H plus, the Broncillary acid donates H plus and a base accepts it. So we talk about a proton donor and a proton acceptor. So if we go back to our HCl example, HCl plus water produces hydronium ion and chloride. So HCl donates a proton to water, therefore HCl is an acid. The water accepts a proton from the HCl, so water is the base. Water can behave as an acid or a base depending on the context, and if that's true, that substance is called amphoteric. And water is probably the most common example of that, but anions of polyprotic acids can, like HSO4 minus or something like that, can also be amphoteric. And so if you look at the HCl reacting with the water, what we can see is that HCl reacts with water, it donates the hydrogen to the water, acting as the acid, and water acting as the base. We can look at conjugate acid, conjugate base pairs. Whatever's left of the acid after it donates the proton is called the conjugate base. In the case of our HCl, it was the chloride ion. Similarly, whatever remains after the base, after it accepts the proton, is called the conjugate acid. So if we consider a generic reaction now, HA reacting with water to produce A minus and H3O plus, where you see there's an equilibrium. So this is a weak acid. After HA, the acid loses its proton, is converted into A minus, the conjugate base. And so they are conjugate acid, conjugate base pairs. Go back and review the first semester videos, and I'll try to link it into the course, where it reviews the strong acids and the strong bases. That's going to be important for this chapter, because if they're not the strong ones, then by default they're the weak ones. And so keep that in mind and make sure you review that list. So then the water is acting as a base and it's converted to H3O plus, which is the acid. Therefore, water and H3O plus are conjugate acid, conjugate base pairs. Notice they differ by one and only one proton.